In this lesson, we're going to look at how to create a very simple WebAssembly function. In this example, a function that will take the square root of a number. As you can see here, this function is running as native WebAssembly code in the browser, and we can call it to get the square root. I'm going to be using a project called WebAssembly Explorer, and this allows us to write pure WebAssembly code directly in the browser to get a binary that we can use in our application. Let's jump straight in. Every WebAssembly file starts with a module declaration. We then need to create our square root function itself, and we can do this through a function declaration. We give the function a name, and then inside of the function, we have to say what parameters and return values the function has. For our square root function, we're going to have a single parameter which we can label num. The type of this parameter is a decimal type, so we're going to use the float32 number representation in memory. This means it's a 32-bit floating point number. The result type is also going to be the same floaty32 output of the square root value. With the parameters written, we can now write the body of the function. We want to take the float32 square root of the number parameter, and the way we read that parameter is by using the getLocal function. We can then reference the number parameter by the label we gave it. So we're reading the parameter value, passing it to the square root function, and the result is going to just sit over here at the end of the function and will naturally become the return value, and it's the correct type because it's already a float32. To actually be able to use this function, we want to expose it to JavaScript, and the way we do this is with an export declaration in the WebAssembly module. We can give the export a name, say square root, and then we reference the function by the function label we gave it further down, just like you would exporting a function in JavaScript. Now we can assemble the binary using the in-browser tool, and then we can also download the binary to our file system. Moving this downloaded WebAssembly file to our main project folder, we can then edit our HTML file to load the WebAssembly binary. In order to load the WebAssembly in the browser, we're going to need to fetch and compile it ourselves. So we're going to use the fetch function in the browser to fetch the WebAssembly binary. That gives us back a promise for the response. We need to check that the response is okay, and if so, we can return the array buffer from the response. This is because WebAssembly is a binary format, so we want to use the raw binary bytes. Let's also add a nice error message if the response is not okay. This returns back those raw bytes, which we can then use the JavaScript WebAssembly API to compile into a WebAssembly module. The promise for the module comes back, and we then need to actually instantiate this to get a WebAssembly module instance. So we use webassembly.instantiate. The instance then contains an exports property, which contains all our exported bindings from the WebAssembly module. So I'm going to pick our square root function off the exports and write it to the window object. We can now see our WebAssembly function in the browser. For this lesson, I'm using a project called wasm, which allows me to write C in the box over here and compile it into WebAssembly in the browser, as well as running it to experiment with it. There's going to be many languages that compile into WebAssembly, and this is one of the major benefits of WebAssembly. But if we want to play around with it and understand WebAssembly, C is one of the best levels to do this at because it's a very low-level abstraction on top of the raw assembly code. Let's create, for example, a getSquareRoot function. The return value of this function is going to be a floating point number. By default, float is a 32-bit type, and then we're going to call this function getSquareRoot. The input into this function is going to be a float number again, and then we're just going to return the square root of the number. In C, the square root function is loaded from the math header, so I'm just going to include that header at the top. We can now build the code. At the bottom, our WebAssembly module comes up. We can see that it's exporting our getSquareRoot function, and we can see the function defined over here as well, where it's taking an input float32, returning a float32, and then taking the square root. Obviously, as you write more complicated C code, it gets much more difficult to read this WAST, but there's a very direct translation between the two. If we want to play around with the output, this is a very simple synchronous instantiation of WebAssembly that comes by default when you load up wasm. On this wasm instance.exports, we can access any of our functions in the C code. So I'm going to run the getSquareRoot function over here, and I can call it with any number and then use the run feature. To use this WebAssembly in our own project, I'm going to click the Download WASM button. I'm then going to locate the program.wasm file in the local project and open up the HTML. To load the WASM, I'm going to use a helper function called fetch and instantiate WASM. This will asynchronously load a WebAssembly file from a URL, execute it, and return back the exports of that WebAssembly module. So I can call this function directly, passing the URL of our program file, which is program.wasm, and this will return a promise returning the exact exports of the WASM file. I can then assign our getSquareRoot function directly from the WASM module exports available as the name getSquareRoot. If we run this in the browser, we can see getSquareRoot is now available. When writing WebAssembly, one of the issues we hit is with debugging workflows. We can actually get this raw WebAssembly format in the browser console and step through it, but it's often not very useful for finding a problem. Source maps will be coming, but in the meantime, we unfortunately have to step back to some of the old JavaScript tricks. To debug this getSquareRoot function, what I'm going to do is create a console log function that I can call. And so, for example, if I wanted to know what inputs this function was getting, I want to just log that number. And the way we can create a console log function is by calling this function that actually exists in JavaScript. So we define the shape of this function in C and treat it as an external function. It has no return value, so it's a void. And then the input value is going to be a float number. So we're just going to just define that signature. When we build our WebAssembly, we'll see that this function is automatically treated as an external, and it becomes available as an input within our module. It's importing console log from a module called environment. This is just a default module namespace name for the externals of a C code compilation process. In our instantiation code here, we've got this wasm imports object going into the instance creation. So I'm going to change this to be a direct object literal and set that environment value to contain a console log. Normally we'd set this to the console.log function, but because I'm in wasm-fiddle, I want to use the wasm-fiddle log function, which is just called log. We can now execute this code, and we can see the input value logged before we log the output value. We're running a JavaScript function directly from within WebAssembly. To quickly go through loading this same workflow in our local application, I'm going to download the WebAssembly binary. Switching into the local application, I'm first going to include our wasm helper. Using this helper, I'm going to fetch the program.wasm file that we located in the project folder. The optional second argument to this helper is the imports object. And this is where we can set that environment module. I'm going to set the console log function of the environment module, this time just to be the direct console.log function in the browser. The promise we get back for this fetch and instantiate call is our executed WebAssembly module with the exports available on the object. So I can now call the getSquareRoot function directly with any input value. If I log the output as well, we should see both the input and the output being logged in the browser. Using functions in WebAssembly, we can pass individual numeric values. We're restricted to integers and floats, either 32-bit or 64-bit. The standard wasm-fiddle example has a function that returns a number. When we build and run this, we can log that number. We're passing numbers through the interfaces. But what if I wanted to deal with something like a string of characters? In C, we define a string using a character array. And if I wanted this hello world string to be passed into JavaScript, how might I do that? One option would be to create a function, getChar, that returns individual characters at a single offset. So we're still returning a number representing the character, but we can call it many times to get the whole string. If I return the individual item of the string, we can then call this function from JavaScript, calling the getChar function in JavaScript with 0 to get the first character of the string. We can then see the char code for h being returned. We could then use some code to convert that into the correct string character, and we could read out the string letter by letter. Thankfully, there's a better way to do this. Instead of a getChar function, I'm going to create a char pointer returning function called getStringOffset. What this function will do is it will return the memory address of the first character of the string. When we build this, we can see in the code below, getStringOffset is returning a single number, which is a 32-bit integer. It's a constant integer 16. And this is the address of our string in the WebAssembly memory. If we look further up in this output, we can see that there's a data section. And the data section is used to create pre-allocated memory in our WebAssembly modules. This data section is allocating at address number 16 the content hello world. And then our memory is also being exported over here. So we've got this single piece of addressable linear memory that contains the data we want. So now we just have to write the JavaScript to read it. The first thing I'm going to do is read out that memory export, which is directly the instance.exports memory property. The way that we access raw memory in JavaScript is using typed arrays. So we want to create a typed array on top of this WebAssembly memory that represents our string. Each character of the string is 8 bits. So I'm going to use the uint8 array typed array on top of the WebAssembly memory, the memory.buffer property. I then specify the offset within the WebAssembly memory that our string starts. Calling the getStringOffset function, we can get this address 16. The last argument for our typed array is the length of the buffer. In this case, 11 characters for the string. Finally, to convert this raw buffer into an actual JavaScript string, we use the text decoder API. We pass the raw buffer and it gives us back the string that we can then log in the console. In this example application, I'm calling a console log function within the main function of my C application. This function takes 2 arguments, an offset into the WebAssembly memory, which is the first character of the string that I've defined, and then the length in that memory, the length of the string. When run, this function is defined in JavaScript, where it creates a typed array buffer on top of WebAssembly memory for that offset and length. It then uses the text decoder to decode the string and log the output JavaScript string. We're reading raw data from WebAssembly memory. What if we wanted to write into WebAssembly memory? So as an example, I'm going to consider a function toLowerCase, where we take an input string and we then output an output string that is the lowercase version of it. So we're going to have 2 strings here, and I'm going to say that they're both 20 characters long. In the toLowerCase function, we can now loop over each character of the string. We read the character value from the input string, and we can then check if it's a capital letter based on the ASCII range. This is much faster with bitwise arithmetic, but for clarity, we can just check if it's between the 65 to 90 range in ASCII. If it's in that range, we then just shift it. Once we've got the results in lowercase character, we set that into the output string. To make this really easy to run, I'm then just going to run the console log function on the address of the out string with the total length and remove the main function. To be able to write to the input string in JavaScript, I'm going to create a getOffset function, just like we had before, that returns the address of the input string in the WebAssembly memory. With this built successfully, what we're then going to do in JavaScript is populate that input string by writing WebAssembly memory from JavaScript. We're then going to call the toLowerCase function, and that will then go ahead and log the lowercase output for us. What we'd like to have here is a function that allows us to write a string from JavaScript into that WebAssembly memory. We could then provide an offset of where to write that memory, which we can then get from our getInStringOffset function that we wrote. To create this writeString function, we're going to take its string and offset inputs, and the first thing we want to do is generate the raw byte buffer from the string. To do that, we can use the text encoder interface to convert the JavaScript string into a typed array uint8 buffer, just like we have above. To write to the WebAssembly memory, we're going to create another buffer, which represents that input string WebAssembly memory. We're going to generate it from the WebAssembly memory buffer at the offset of that input string that was passed. We're also going to set it to the length of the buffer that we've just created that we're going to write into it. Looping through each byte index in the string buffer, we can then set into the out buffer, which represents that input string in WebAssembly memory, set each byte from that string buffer. By writing directly into the WebAssembly typed array, we're writing directly into WebAssembly memory. Running this, we can see that it's correctly lowercasing the input string that we've set from JavaScript, including some null bytes at the end because we've padded it up to 20 characters. It's worth noting here that there's quite a bit of performance overhead to this copying of memory that's going on between JavaScript and WebAssembly. For this reason, it's worth thinking about where a piece of memory belongs as its source of truth quite carefully, and letting it always stay there as the main source of truth to minimize the copying operations. For a simple example of dynamic memory allocation in WebAssembly, let's consider that we have a record data type, which has some arbitrary fields associated with it. Say, for example, an ID, an X, and a Y value. To dynamically create one of these records, we're going to use a createRecord function, which will take its fields as its arguments. And then we can use malloc within this function to create the memory for each record. We need to pass into malloc the size of the record in bytes, so we can use the size of operator here. The value we get back is then the memory address of the new record, which is therefore a pointer to a record. We can now use this pointer to set the ID, X, and Y values directly into that new memory address. Finally, we will return the memory address from the createRecord function. So the function is therefore returning a pointer to a record. To create a deleteRecord function, this is going to be a function with no return value that takes a record address in memory and then calls free on that memory address. Of course, there's more efficient and much better ways to do this, but this is just for an example. In order to use malloc and free, I'm going to include the standard library as well. Taking a look at the generated WebAssembly code, we can see that the free and malloc functions are both treated as imported functions. It's up to us to link them in ourselves. The memory is being exported, and then we've got our createRecord and deleteRecord functions defined. Looking at the deleteRecord function, we can see that it's taking a 32-bit integer as its argument, which is a memory address in WebAssembly. It's then calling the free function with that argument number from the local parameter. Briefly looking at the createRecord function, we can also see that it's calling malloc, storing it in a local variable, number 3, which is defined over here. And then it's using the f32.store, i32.store, and f32.store calls to do our record saves in memory of the ID, X, and Y values that were passed as parameters, before finally returning the memory address, which was stored in the local variable. Let's download the WebAssembly code and get this wired in. In my local project, I've included the fetch and instantiate wasm helper, which I'm going to use to load the local program.wasm file that we just downloaded. For the imports object, I'm going to need to pass an environment import, which contains the malloc and free implementations. I'll get to that in a moment. This promise resolves to the WebAssembly module exports, which contains our createRecord function. I'm just going to call this with arbitrary values and then log the result. For linking in malloc and free, I've actually already pre-built from C into WebAssembly a malloc and free implementation, which I'm just going to load from the existing file at memory.wasm. The link to this file is included in the lesson description. This memory.wasm file takes a single environment import, which sets the memory. The reason for this is that malloc and free both need to act on the program's memory, which is defined in the program itself because it exported its own memory. We can only work with a single memory at a time in WebAssembly, at least currently, so we want to pass that program's memory into the memory's memory. So I'm going to access that from m.memory where it was exported. The module value that we get back for memory.wasm then contains our malloc and our free functions bound to the program's memory. How do we get these malloc and free functions into the imports of the program.wasm? Well, I'm going to use an indirection here by creating temporary placeholders for these functions called wasm malloc and wasm free. In the environment imports to program.wasm, I'm actually going to create a JavaScript implementation of malloc that takes a length and returns the wasm malloc result applied to that length. And the same for the free function, which will take an address and return the wasm free of that address. We now just need to assign the wasm malloc from the version that we got back from the memory, and the same for the wasm free implementation. Lastly, I'm just going to make sure we're calling our createRecord function only once everything has been set up. When we run this, we can see that we're getting a dynamically allocated memory address. I have done some performance measurements to see what the cost is of these JS bindings. Because we're not linking directly to the WebAssembly function, we're jumping through JavaScript. There's a very, very small performance overhead on my tests of about 5% on otherwise very highly performant code. If that's something that worries you, a better thing to do here is to have program.wasm as well import its memory. There's another performance concern in this code, which is that we're fetching program.wasm, and then only once that is fetched and compiled are we fetching memory.wasm. What we really want to be doing is fetching in parallel so that we utilize the network as best as possible. We can adjust this fetch and instantiate wasm function to convert it into a parallel fetch and compile function that will instead take an array of URLs to fetch and compile. We use this to fetch program and memory in parallel, then we need to call webassembly.instantiate ourselves. This takes the imports object as its second argument, so the rest of the code is actually much the same. I'll just copy all of that in. Then the final difference is that the return value of webassembly.instantiate is a module object, so we need to access the exports property on that directly. And that gives us the parallel loader. There's quite a complex instantiation process going on for loading program and memory.wasm together in this application. And the reason for this is that program is exporting its memory, and then memory needs to import that same memory. So we instantiate program first, take its memory export, which is m.exports.memory, and pass it in as the memory import when we instantiate memory. Another way to do this is to create the memory in JavaScript before instantiating the WebAssembly modules. The WebAssembly memory constructor takes a single argument, which can then set the initial memory size in WebAssembly pages. WebAssembly pages are 64 kilobytes, or 2 to the 16 bytes, so one will be more than enough for this application. With the memory now created in JavaScript, we can then pass it in to the memory import when we instantiate the memory module. We'd like to do the same for the instantiation of the program module as well, because we need all of our modules to be sharing the same memory in this example. Unfortunately, program doesn't have a memory import because it was compiled with a memory export, which by definition means it has a different, separate memory. We're going to need to recompile program to support this. From the original compilation, I'm going to take the WAST output and copy it into WebAssembly Explorer. In WebAssembly Explorer, we can edit this WAST output. So I'm going to find that memory over here where it's defined, and I'm going to remove the memory definition from inside the module and convert the export memory into an import memory. We need to import memory from the module called environment because that's where we're importing everything from. And then I'm going to replace this memory declaration with a memory declaration including the initial size, which is that first parameter 1. I can then assemble and download this converted binary. When compiling locally, there is an import memory flag for doing this automatically. Returning to the local application with the new program.wasm wired in, it'll now accept a memory import under the environment namespace. I can now simplify this instantiation by first instantiating memory, and then with the memory module that we get back, we can pass the memory.exports.free and malloc directly into the program imports because it's already bound to the same memory the program's using. With the resultant instantiation of program, we've then got our final module value and a much simpler instantiation process. There's a little bit of work to wiring these WebAssembly modules together correctly here, but the benefit is we're able to finally control the bootstrap of our application for our exact needs. If you are looking for a comprehensive solution for managing the setup of WebAssembly, I highly recommend trying out mscripton, which comes with standard C, C++ application compilation out of the box, taking care of all the wiring itself. There's a link to the project in the description. I've got a file located in native demo.c, which we're going to compile into WebAssembly. I've got my WebAssembly build of llvm located at llvm wasm, and I'm going to use the bin clang driver to be able to do this C or C++ compilation. When we run clang, we can't convert directly into WebAssembly yet. So for now, what we have to do is output an intermediate S format. This is the emit llvm flag for clang, or we can just use the shorthand capital S. I'm then going to apply my C optimizations, and I'm going to choose the target to be wasm32. By default, wasm is a 32-bit system. That may well change in future. I'm then using the C flag to compile the file at native demo.c, and then finally output that into a temporary file demo.s. Ideally, this would be in a temporary folder or something like that. When we run that compilation process, we'll see if there's any warnings or errors, and then we can see the final demo.s file contains this intermediate llvm format. To convert this llvm intermediate format into WebAssembly, we use the binaryen project, which comes with a tool called s2wasm. I'm going to call this against the demo.s file, and I'm going to pass an s flag to set the stack size. I strongly recommend remembering this flag because otherwise code will randomly break. And I'm going to set a stack size of 0.5 MB. It's the size in bytes. And then we're going to output into a demo.wast file. If I wanted to compile my WebAssembly module to import its memory instead of exporting it by default here, I could pass an import memory flag. For now, I'm going to compile with the export memory option. If we look at demo.wast, we can now see that this is a WebAssembly module. We have our function exports, our memory being set up, etc. The last step is to convert this WAST file into a WebAssembly binary that we can run in the browser. This is where we use the third tool from the WebAssembly binary toolkit called wast2wasm. And I'm going to run that against demo.wast, outputting a demo.wasm file. If we look inside that demo.wasm file, you can see it starts with an asm header and it's all binary format ready to run in the browser. One of the first problems you run into with this kind of a compilation process is if I try and compile a different demo that uses the standard library, we'll see that we immediately get an issue trying to compile with a standard library. It won't find it. Because WebAssembly is so new, we need to configure the standard library ourselves. This is where it can be useful to use an all-encompassing tool like Emscripten that can handle all of these details for us. What I found works quite well here is linking against Emscripten's version of the standard libraries. Because it's a large download to clone Emscripten from GitHub, I've actually just hacked together a repo that contains just these include folders. If we clone this, we can then use this as our import target to get some basic standard lib support. When running our clang build command, we add the include option, capital I, and then can load this include folder either using libc or libcxx or both to get standard library headers that can then fix the build. Before installing llvm, we want to just check a few prerequisites. You should check that you have GCC installed, a version of make, and a version of cmake as well. If you don't have GCC or make, then it's advisable to run scode select install on Mac to make sure you've got the Xcode command line tools. And in Windows, we want to have Visual Studio installed. For cmake, you can download this from the website in the documentation of this lesson. So I'm going to start off by cloning llvm, and I'm going to use a mirror just so we can do this via git. Once that's complete, we can go into this llvm folder, and then within the tools folder, we want to clone clang. Again, I'm going to use the llvm mirror. With clang installed, I'm going to back out of this tools folder, and then I'm going to make a folder below the llvm folder called llvm build. Within this folder, I can now use our cmake command to set up the build. Here's the command we're going to use. In Windows, this Unix makefiles would be Visual Studio instead. I'm building into another folder called llvm wasm, which is going to contain the final build output. We're removing all the targets. We're building for the wasm32 architecture as a WebAssembly target from the source in the llvm folder. Once cmake completes, we can then actually begin the build process, and this is going to take about an hour or so. I'm going to use the J8 flag so that we run make in parallel and then a make install. In Windows, I would have needed to have opened Visual Studio and opened the llvm.sln file to start the build from there. When the build eventually completes, we can check that we've got our C compiler available at llvm wasm bin clang. To free up some space, this llvm build folder can then be removed. To get the s2wasm tool, I'm going to clone and build binaryen from GitHub. In the binaryen folder with cmake installed, we then run cmake dot, and when that's ready, we run cmake --build dot to build the current folder. For Windows users, if you've installed cmake and have the Visual Studio build tools, the same sort of process should work. To build the WebAssembly binary toolkit, I'm going to clone from GitHub. We need to add this recursive flag when we do that clone to make sure we include the submodules. Once that's downloaded, it's roughly the same build process, except this time I'm going to create a build folder running cmake within it. I'm going to add the cmake executable output path flag to output our executable binaries into the out folder. We run that against the lower folder source, and then we run cmake --build dot to complete the build into the output path. The build folder can then be removed afterwards. We're going to use a typed array to render a number of circles directly into the page with incredibly high performance. We've got a canvas inside the body, and then I'm importing a render function from a local render module, which we're just going to treat as a black box. This render function takes the circle data as its first argument and the number of circles as the second argument. As a first example, let's just render a single circle. That circle data is then exactly our typed array, which represents its position and size on the screen. This position data is decimal data, and so uses the float data type in memory. Each circle is based on 3 numbers: its x value, its y value, and its radius, which are each going to be these 32-bit floating point numbers. Let's set the circle initially where its x value is at 0, its y value is at 0, and its third slot, the radius, is set to 100. That typed array data then gets copied straight to the graphics card and drawn to the screen. Let's position the circle randomly within the page. The third argument to the render function is an init method, which will get the display width and the display height as convenience arguments. We can then move our assignment of the circle positions to within this init function and set the x value to a random point within the width of the page and the y value to a random point within the height of the page. To then draw any number of circles, we need to make our init function dependent on the circle count. So in our initial data allocation, we're going to allocate an x, y, and r value times the number of circles. And then within the init function, we can do a loop from the first data point of the first circle through to the last data point of the last circle, incrementing 3 points at a time for each circle. We can then update the indices to be relative to the current circle. And let's try rendering 10 circles. To add dynamics, the fourth argument to our render function is a time step function. This has the same signature as our initialization function, except it allows us to then modify the data positions on each frame. If we just re-randomize the positions, we'll get something quite catastrophic, although it's no problem at all for the WebGL renderer. To properly have dynamic movement, we want to store the velocities as another data point associated with the circle, as well as its x, y, and r value. We can't include this in our current circle data because this represents a single piece of continuous memory that's sent to the GPU on render, and it needs to be as compact as possible to only send what's necessary for rendering in order to get the best performance. So we're actually going to create a separate typed array which is going to contain the velocity values. And so we just need to have 2 values within this float32 array. They're still 32-bit floats because they're decimal values. Now in our initialization function, we can set the velocities to random x and y components. In order to index the velocities, we're going to need a new index counter. Because the velocities move in sequences of 2, we need to index through in an order of 2 for these. And then in our time step function, we're going to increment the x and y components by the velocity values. And we again add the separate increment of 2 for the velocities array. I'm just going to remove this unnecessary reassignment and add some edge detection. If the x value of the circle is greater than the display width or less than 0, we're going to flip the x component of the velocity, and the same for the y component. We can polish up the exact bounds later. For now, let's test the performance. Decreasing the circle radius, let's start upping that circle count. Lowering the radius again, we can try 1,000. 10,000. And lowering it even further, we can see if we can get to 100,000. Or even 1,000,000 circles being rendered. By using typed arrays and very simple operations in JavaScript, we've been able to write very, very low-level code that acts directly on top of memory. Combined with the WebGL renderer, this is what gets us the incredible performance. We're going to take this JavaScript application that renders circles into the page and convert it into WebAssembly. All the data for the circles is stored in a single circle data typed array, which contains an x, y, and r value for each circle that is rendered into the page. Our initialization function sets that initial state of the circles, and our time step function then updates the positions based on the velocities and bouncing off the edges. The details of the functions aren't actually that important. For the conversion into WebAssembly, the important thing is how this code interfaces with JavaScript and how we manage its interface. We're going to do the conversion into C. We create a new C file, and let's just copy and paste all the JavaScript except for the render call directly into the C file. We can now start the conversion. The circle count is going to be a constant of our compilation process, so we'll set it up as a macro. For the circle data, we could just set it up as an array of floats like we've done in JavaScript, but in C we can do better than that. The x, y, and r values of each circle can be represented in a C struct. With each entry set as a float data type, it's still effectively the same representation in memory as 3 floats in a row we had manually in our typed array. The velocity data can then be stored in the same way, with the x and y components of velocity as floats. To actually initialize the circle data, we need to create an array of these circle structs. The way we initialize that in C is with the struct circle and then the name of the array that we're creating. We're going to statically set aside the full amount of circles, which is 1,000, times the size of the circle, which is 3 floats. So we end up setting aside the same amount of memory as we did in JavaScript with our explicit initialization, but with C it knows the size of the object, so we don't need to add our multiple of 3. We can do the same for the circle velocity. And now we're ready to write our init and time step functions. Converting their signatures into valid C function signatures. Both these functions have no return values, so they're void. And then the display width and display height are both float arguments. To iterate over the array of circle data, we no longer need to do this complex iteration. We can simply have a single integer which is iterating over the full circle count and incrementing by 1. C can take care of the rest for us. Updating the indices, we then can access our struct items individually. So the first item is now called x. We no longer need to do a custom increment. We can just represent the y value as y and the r value as r. The same for the velocity data. And let's apply the same conversion to the time step as well. These constant values are all 32-bit floats, and then we just update the indices. The last part of this code that's still JavaScript is these math.random calls. We're going to still be calling math.random underneath because we don't have access to another random source in WebAssembly, but we're going to make it as an external function. So we can just define our math.random signature as returning a float value, and then we can call it randomf. By simply defining the signature, it'll be treated as an external function, and we can then replace those calls. This C file should really remain the source of truth for where the circle count is defined. It's annoying to have to define it as well within the JavaScript. So let's create a function that will simply provide that. In order to actually get our data out of WebAssembly, we need to know where the address is to the circle data object. This is the thing that we want to have access to from JavaScript. So I'm going to create a helper function that returns an integer called getCircleDataOffset. The return value is the memory address of the circle data array. When compiled, this will become the exact WebAssembly memory address. To quickly compile, I'm going to copy the C code into wasm fiddle. Once the build completes successfully, the WAST format comes up at the bottom of the page, and we can then download the WebAssembly binary file. Checking the WAST output, we can see that we're importing the random f function from an environment module that we're going to populate shortly. We're also exporting our memory as well as all of the functions that we've created in our C file. In a new file, let's now wire in the WebAssembly. First, copy in a helper function to load the WebAssembly. And then I'm going to call it with the path to our WebAssembly file, which I've located in a folder called libdynamics.wasm. The second argument contains the imports for the wasm module. We need to set the environment import, which contains a random f function, which we assign from math.random. This returns a promise which resolves to our instantiated WebAssembly module. Let's work backwards from the arguments to our render function. First thing we want is the circle count. We can get that by calling the getCircleCount function that we created directly off the WebAssembly module instance. In the same way, we can call the getCircleDataOffset function to get the memory address of the circle data array in wasm memory. To get our circle data typed array, we can use a different form of the float32 array constructor. This allows us to create a typed array from any buffer source. In this case, we can use the exported memory object from the wasm module, accessing the buffer property. This constructor form then takes two further arguments, the offset in bytes within the buffer and the length in bytes within the buffer to generate the typed array from. The offset is exactly our exported offset, and then the length is exactly the length that we had at the very beginning, the number of circles times 3, the total size of our circle position data in memory. Our init and timestep methods can then be accessed directly from the instance exports, completing our WebAssembly conversion. In this example, we're calculating the collisions between the circles on the page, which adds quite a performance overhead. If I increase the circle count to just 2000, we can already start to see a significant slowdown. So let's see if our conversion to WebAssembly can make this faster. Without going into the details of the collision algorithm, we're just going to copy the JavaScript into our C file to begin the conversion. To go through the steps briefly, define circle count as a macro, update the function signatures, add types to our variables, fix up the iteration, define our external math functions and update their calls, add includes for the math and standard bool libraries. Our use of square root, pow, and ceil can then be inlined by the compiler by using these functions. Next, define our circle and circle velocity structs, and initialize arrays of these of length circle count for their static allocation. Add a getCircleCount function and a getCircleDataOffset function to know where to find the address of the circle position data in wasm memory. Finally, we fix up the index access within our circle data struct arrays to correctly reference the data values. We can then compile using wasm fiddle, downloading the final WebAssembly binary file. In a new page, I can now include the wasm helper and use that to load the WebAssembly binary, which I've located at dynamics.call.wasm. The second argument to this function is the imports. We need to set the environment, which contains a random f and the exp function. The promise gives us back the instantiated module, and we can then read off the circle count and circle data offset from the functions that we exported. We can construct our typed array data for the circle data using the offset that we've been provided, as well as the fact that we know that it's going to be 3 times the circle count in length in the WebAssembly memory. Finally, we can render that circle data passing the init and timestep methods from our WebAssembly binary into the render function. Putting the JS simulation on the left and the WebAssembly version on the right, we can compare the performance directly. The unfortunate truth is that the JS version on the left actually ends up still faster than our WebAssembly. WebAssembly isn't a silver bullet for performance. It may just be that we're in the early days of optimization for WebAssembly in browsers, but we can get past this today if we approach performance with the right principles. To optimize our collision algorithm in JavaScript, our main loop is this timestep function. What we're doing on each time step is we're looping over every single circle in the entire page, that's 2000. We're updating its dynamics, and then we're applying collision detection against every other circle. We're doing 4 million collision detections every single frame. And this is exactly our performance problem. We can improve this collision algorithm by breaking the space up with the grid. We then only need to compute collision detection within individual cells with the grid. I'm going to use an arbitrary width and height for the grid initially. We can optimize this later. In our time step function, we then create the grid on every single time step. We loop through the columns and the rows, each of which is represented by an array. The individual cells are then an array of circles that are contained within that grid cell. For this initialization step, we're just going to set it to an empty array for each cell. The first part of our time step function is computing the dynamics of each circle. We're going to leave this computation in place, but then instead of going straight into the collision detection, we're going to first assign each circle into one of the grid cells. We compute the column for the current circle based on its x position in the page as a fraction of the total width, scaled up to the grid size. We need to round that down since the grid starts at 0, so we can do that using math.floor. If we look at some of the bigger circles on the right, they're actually contained in multiple grid cells. So instead of computing a single cell for each circle, we need to compute its cell range. We'll compute its leftmost column based on subtracting the radius from the center point, then also compute its rightmost column, and do the same for its topmost row and its bottom row. Now that we know exactly which cells the given circle belongs to, we need to assign it into the grid. We can do a loop over from the first column to the last column that the circle is in, and then we take those columns directly from the grid. We then loop the row from the first row that the circle's in to the last row the circle's in, and we get the cell value out of the grid. We pre-assigned already each cell to an empty array of circles, so we can just use an array push to add the circle to this cell. To reference the circle, we can use the index of the circle in the circle data array as our unique identifier. If the circle happens to be outside of the browser bounds, say we're resizing the browser window, we're going to be assigning it to an invalid grid or negative grid value. So let's just detect if the from column's negative and set it to 0, and similarly if the to column is greater than the grid width, just snap it back to the grid size. If two circles collide outside of the browser window, we're effectively ignoring those collision detections. With the grid, we no longer need to do collision detection between every circle. So I'm going to close out this loop over every circle that we're currently in. Now we just have to loop over each of the individual cells on the grid and apply collision detections for the circles just within that cell. The cell value itself is the array of circle indices which are contained in the cell, so we want to loop over this array as well. The iteration values we had for each circle before were an I and an IV iterator, the I going in steps of 3 and the IV going in steps of 2. To get the IV iteration value from the information we have here, I'm just going to divide I by 3 and multiply up by 2. As in the previous code, we can now read out the X, Y, and R values of the circle from the circle data, as well as reading out the X and Y components of the velocity using these indices. With the variables set up for one circle in the cell, we want to do a comparison with another circle in the cell. So we're going to need a final inner loop where we can get the index of the circle that we're comparing with. This loop only needs to start from the circle after the current circle, so we only do each pair of comparisons once. We're just about there now. With these J and JV indices set up for the comparison circle, the position and velocity lookups are actually already in our original collision detection code. So I'm just going to go ahead and copy that in. This is now nesting our entire collision detection algorithm within these specific grid cell comparisons. And that's the collision algorithm grid optimization. I can assure you I didn't get this right first time, and there were many hours of reading, rewriting, and debugging in the process. On the right of the screen over here, I've got the optimized JS collision detection algorithm. And on the left, we've got the C code for the unoptimized version. I'm going to bring across the optimizations from the JS version into the C code so we can get our optimized collision algorithm in WebAssembly to compare the performance. If you're not very familiar with C programming, please don't worry if you don't follow every single detail here. The first difference between the two is on the right, I've got this grid width and grid height being defined after the circle count. I'm going to define those in the C code. The rest of the code for the grid optimization is in the timestep function. We create the grid, initialize the grid, and then we start assigning the circles that belong to that cell in the grid. Starting with the initialization, we can create a grid in C using a multidimensional array of the grid width and grid height. And this will give us the same sort of thing that we had in JavaScript. But the value of each grid cell in C can't just be an arbitrary array of circles in that grid cell, because we don't have arbitrary length arrays in C. The lazy option would be to just assign the maximum amount of memory. We could say that there's never going to be more than 1,000 circles in a given grid cell. And so we just make every grid cell an array of 1,000 circles. The reference for each circle that we used in the JS code is that each circle was referenced by its integer index. So we'd have 1,000 integers per grid cell. This is a terrible waste of memory though. Instead, a better data structure that we can use is a linked list. The principle of a linked list is that instead of storing the index of the circle for each cell, we create a record data type which contains that index and then also has a pointer to another record for the next record in that cell. The pointer is a memory reference to another record of exactly the same type. When we no longer point to anything else, we know we've reached the end of the list. This way, any number of individual circles can be referenced from a single grid cell. These cell circle records then need their own place to be stored in memory. I'm going to initialize a set length of them using an array. A given circle is never going to belong to more than 4 grid cells at a time due to the design of the grid size. So the amount of memory I'll set aside for this is the number of circles times 4, as we'll never have more records than that. The grid itself now becomes the first layer of our linked lists. Each grid cell corresponds to a pointer into the first record, and from that record we can follow the next cell records to get the full list of circles in a given cell. That completes the data structuring. We can now move on to the initialization step. The loop over the grid cells remains much the same, except we don't have to cache the columns anymore for performance. To set the individual grid cells to an empty list initially, I'm going to use the null pointer. This is just a 0 memory reference. To use this, I'm going to have to include standard def.h from the header files. Next, we move on to the code that allocates each circle to a grid cell. I'll copy that in directly and just update it to represent valid C code. We determine the cell range of the current circle and then loop through that range, assigning it to each of those grid cells. The assignment we'd like to be making here is to set a new record into the grid which represents this circle within this cell. In most cases, there will already be a record in place, so this is where the linked list comes in. We have to set the next value of the current record to the last record that was in place, so we chain on and amend the list each time. And the record also contains the index of the current circle. The cell circle record is instantiated as a struct. I've glossed over a detail here in that the grid values were memory addresses of the individual cell circle records. So this needs to be a pointer, and then we need to use the pointer struct access for these assignments. What does this pointer point to? Well, we already allocated all the space in memory for these cell circles as the cell circles array. So the pointer can be set to reference an exact record in this memory. Ideally, we want to allocate from the first record to the last. So I'm going to create a counter that allows me to determine how many we've allocated, and then we know the next one's just at that count, which we can then increment each time. Now for the collision detection algorithm, I'm going to copy the loop over all of the grid cells from the JS optimized version and update that to the C code. Let me just correct those grid width and grid height names as well. When reading the grid cell, this is now the pointer to our cell circle record. So we're going to instantiate that struct pointer. Then looping over all the records means looping over those next values. So using a while loop, we can then keep updating the individual cell circle record to the next record in the list. copying over the inner part of the loop, I'll update these variables for the index, position, and velocity values of the current circle. For the loop over all of the next circles in the cell, I'm going to start with a j cell circle equal to exactly the I cell circle. In the while statement itself, I'll update the next value and check that it's not the null reference before continuing the loop. This way, the j circle that we're comparing with is the one after the current circle, as it should be, and it's a little bit less code to write in the loop. With the optimization loops complete, lastly, we need to include the collision detection code, which is already in C. Once that's in place, the optimization is complete. Upping the circle count before compiling, let's now compare the performance. The WebAssembly version on the right is now faster than the JavaScript version on the left. It's our ability to create more efficient data structures in WebAssembly that gives us the true performance benefit.